Okay, so yesterday we started building the spectrum. We were doing the canonical quantization. We promoted the oscillators to operators. And so the different, the new thing regarding the bosonic string is the fact that we have two sectors, the Neveu-Schwarz sector and the Ramond sector. And these are very different. So in the Neveu-Schwarz sector, it is very much like the bosonic string. We have a ground state. Is labeled by the momentum. And the ground state is annihilated by all annihilation operators. And also the periodic oscillators. And remember, in Neveu-Schwarz, the modes take half integer numbers. Okay, so it's easy. We saw the ground state is a scalar, it's a spin zero state. So and we build the excited state acting on this ground state with racing operators. And the DR. Okay, so this is very much like in bosonic string. Now the difference was the Ramond sector. In the Ramond sector, we found that the ground state was a spinor. We saw it was degenerate because we had these B0 operators which satisfied a Clifford algebra. So acting with different numbers of B0 operators, we created different ground states. So basically we could write it like this. So we had a highest weight state that was annihilated by all the B minus, and then over it, acting with the B plus, we could construct all the two-dimensional representation of the Clifford algebra. Okay, so this is basically the way in which we construct the spectrum. But we still have to impose the physical state conditions. Okay, so these states are not all physical. We have to impose the constraints that were coming from the vanishing of the energy momentum tensor and the supercurrent. And so we also worked out the. I don't have the. No tengo
the pointer.
Okay, no. We worked out the superconformal algebra. We will write it here. So we have the standard Virasoro algebra. And the difference here with the bosonic string is the central charge. So the difference is the central charge. It depends. This phi here is the phase that we used. We took phi equals 0 in the Ramond sector and phi equals a half in the Neveu-Schwarz sector. And this is different from the bosonic string. Remember, in the bosonic string, the central charge was d over 12. And this is different because now the fermions are contributing. So each boson contributes 1 to the central charge, and each fermion contributes a half. So that's why we get d over 8. And have the commutator Fm with the modes of the supercurrent. Again, this is and the anticommutator. And this also gets a central charge. Okay. Okay, so this is, we got up to here yesterday. And so now we are going to use, the, but it's also not working. Okay. So on these states that we write, so on the ground states, both of the Schwartz and the Ramon sector, we act with the creation operators, but then the physical states have to satisfy the physical state conditions, which are those over here in the Schwartz sector. The positive modes of the Virasoro generator annihilate the states, and also the positive modes of the supercharge annihilate the state, and we have L0 plus the normal ordering constant equals 0. Here I will call it, yesterday I called it mu, so that we don't make a mistake with the L. So, and this is in the Schwartz sector. Whereas the difference in the Ramon sector is that the moding is integer. So again, this is the Schwartz. I'm writing this in Spanish. Okay, I guess you can know this. And here, notice that this condition also includes the zero mode in the Ramon sector. Okay, the modes of the supercurrent annihilate the physical states, including the zero mode. And then notice that in the Ramon sector, I do not include a normal ordering constant. Okay, I will now tell you why. Okay, so there are several reasons why I didn't include it. First, if you look at the superconformal algebra, G0 squared equals is proportional to L0. Okay, so if we have L0 minus G0 squared physical state equals 0, then we also need G0 minus constant equals 0, but G0, I will write it here. If you remember the expression of G0 in terms of oscillators, it is the sum over the integers, alpha minus m. So there is no normal ordering ambiguity. It is a bosonic oscillator times a fermionic oscillator, so there is no ambiguity. I mean, I can summing over all, and this is it is easy to normal ordering. Okay, so this is one reason. There is no normal ordering ambiguity, and moreover, G0 is anti-commuting, whereas the normal ordering constant is C Lambert. So okay, so we cannot have normal ordering constant in the Ramon sector. Okay, so And then now we will discuss the spectrum and we'll see that it is the correct. And okay, so we have to impose these conditions on the Neveu-Schwarz sector, these conditions on the Ramon sector, and for the closed string we also have the level matching condition, which states that L0 minus L0 T on the physical states equals 0. Okay? So we now have to impose these conditions. Now let us consider the ground state in the Ramon sector, which is basically this here. So we have to impose this condition in the Ramon sector also for G0. So notice that if I do that, G0 is written there. So if I write G0 on the Ramon ground state, I call it this. Okay. So since all the positive modes annihilate the ground state, then this condition here is basically only the zero modes contribute. Okay, and remember the zero modes in the Ramon sector, we had identified them with the gamma matrices. These zero modes satisfy the Clifford algebra. So we said we can give a representation of the zero modes in terms of the Dirac gamma matrices. So this condition is basically, and alpha naught is proportional to the momentum. Okay, so this is basically this condition. On the state, and okay, so I don't go. So, and this has to vanish. And this is basically the Dirac equation. Okay, so I can introduce a polarization, and then this condition here. If I choose a normalization for the state, this is the condition, the physical state condition on the Ramon ground state is the Dirac equation. Okay, the massless Dirac equation. Okay, so we said that the constraints arising from the superconformal algebra were enough to cancel all the negative norm states in the theory. We have these constraints arising from the vanishing of the energy momentum tensor and the supercurrent. We have to impose these constraints on the physical states. And similarly as in the bosonic string, there is a no-ghost theorem stating that these constraints are just enough to decouple all the negative norm states. There is a theorem. I'm not going to prove the theorem, but one can show that the ghosts decouple for a critical dimension, which will turn out to be d equals 10, and for a particular value of the normal ordering constant here in the Neveu-Schwarz sector. Okay? This works the same as in the bosonic string. For the critical dimension and for a particular value of the normal ordering constant, the ghosts decouple from the theory. Son índices espinoriales, ¿no? Lo dijimos. El producto punto son los índices espacio-tiempo, ¿no? Acá hay índices, estos operadores tienen índices espacio-tiempo, pero además como este lo identificamos con la gamma, esto tiene también índices espinoriales. Okay. Okay, so we will find that the critical dimension, which determines the decoupling of gauge, is 10, and this normal ordering constant is -0.5. We will derive it some other way. Okay. So instead of proving the no-gauge theorem, what I'm going to do is I'm going to construct the spectrum in the light cone. I think the same thing was done for the bosonic string. It is easier. I will show you how it works. The light cone breaks the covariance of the theory, so one can also do a covariant quantization, which is better in a sense. But the light cone has the nice property that it gives us directly the states, the physical states. We do not need to impose. So this, the Villasoro constraints are built in the oscillators, in the operators, so we do not need to impose them on the states. Okay? So I'll show you how to do that. So in the bosonic string, I think you have discussed that there is, even once you fix the conformal gauge, there is still some residual symmetry. So you can fix the conformal gauge, fix the two-dimensional metric to be the flat metric, but still, once the metric is fixed to be flat, you can still do some reparametrizations that leave the metric flat. So there is some residual symmetry. So the gauge is not completely fixed, and we can use this extra gauge freedom to fix one coordinate. So in the bosonic string, you define the light cone coordinate. This plus means it's not less, say, x1. So I define a light cone coordinate on space-time. Remember, we had defined the sigma plus minus coordinates on the worksheet, but these are light cone coordinates in space-time. So it combines the x naught, the time-like direction of the axis, and one space-like direction. So in this way, I'm somehow, when I fix this coordinate, this normalization, so I will fix this x plus to be proportional to tau, the time variable on the worksheet. Okay, so this is the same one does in the bosonic string, and by doing this, one is breaking conformal invariance because I am choosing two directions at random, and I'm fixing it to be proportional to tau. Okay, so so this this choice fixes the gauge completely in the bosonic string, but in the superstring we still have some possibility. We still have some freedom of supersymmetry. We can still make some redefinitions of the supersymmetry parameter, and this allows us to also get rid of the psi plus. So I can use that gauge freedom, which is left. I can once I fix the gravitino equals to 0 using the supersymmetry of the theory, I still am left with some extra transformations I can do on the supersymmetry parameter, which keep the gravitino equals 0. And I use that freedom to fix, to eliminate the psi plus component. Psi plus means psi 0 plus psi 1. Again, this is a light combination in space-time. Okay. And this, this implies that the oscillators of this psi naught and psi 1 can be combined in this psi plus, and this all vanish for life. Okay? Okay, so I choose this gauge, I break conformal invariance, I'm sorry, I break covariance because I'm privileging one direction, but okay, I can do that. In the bosonic string, this one fixes the gauge, then one computes the Lorentz algebra, and one recovers the Lorentz algebra in the critical dimension. So that is one way to compute the critical dimension. Here, the same thing. You can compute the Lorentz algebra, and to recover the Lorentz algebra, you need to impose d equals 10. I will find this dimension some other way. Okay, so we do this, and then in this gauge we can compute the Virasoro generators. So we have this constraint, t plus t minus equals 0, and so I can explicitly write t plus plus is t plus x. X plus, okay, so I won't write because it also has the contribution from the fermions, but then I can use this condition since x plus is fixed, then I can combine using this condition. I can obtain d plus and d minus of x minus in terms of the transverse oscillators. Okay, so I can completely eliminate these longitudinal oscillators, and I get okay, so this index I here means these are just the space-like, the space indices. Okay, so this I takes values 2, 3, up to d minus 1. So in this way, I have eliminated this x plus, because, okay, so notice when I take the derivative, plus or minus, it only acts here, and it leaves only the t plus, which is clearly here. So then I have the contribution of the x minus, x plus is fixed, and x minus is expressed in terms of the transverse oscillators. Okay, so I have eliminated the longitudinal oscillators, and similarly for the supercurrent, I have again this condition. Conformal to 0. Then I have already eliminated psi plus and psi minus. Then it can be written again in terms of the longitudinal modes. Okay, so now I have all the oscillators written in terms of the longitudinal, of the transverse oscillators. So I have eliminated the time-like oscillators, which were the ones that were giving us negative norm states. And all the states will be created with these transverse oscillators, and will be they will all be the positive norm states. Okay. Okay, so I won't write this expression because this is too long unless you want me to write it, but it's, I know it's what. Okay, so now it's basically this equation here. I can express it in terms of the operators. Alpha minus is expressed in terms of the alpha I j and bij, and plus the normal ordering constant for m equals 0. Okay? Shall I write it? And similarly for the fermionic oscillators, they are written completely in terms of the transverse oscillator. Okay? So all this is for the open string. For the closed string, we have the same thing for the right movers or the left movers. And then the difference, there's also a difference in alpha naught because of the normalization of the momentum. There is a 1/2. Okay, so
¿Eso fue hallado para los dos sectores o solamente para NS o para
para los dos.
Esto es, la expresión es igual.
Sí, esto es a partir de esta definición y para cualquier desarrollo es. Okay, so now we also have the level matching. The level matching constraint, which is L naught minus L naught tilde. Level matching constraint means that the level number operator for the bosons, now we will only have the contribution from the transverse oscillators. That's why I write transverse. And this has to be equal to the number operator. And I also said yesterday that the normal ordering constant in the left and in the right we take them to be the same. So we have the mass operator will be basically 2 times transverse plus n transverse b, and this has to be okay. So I call it mu, and then this will be for the, say, for the left mover, for the right mover, and the same thing for the right mover. For the right mover, okay? So now we have to determine this normal ordering constant. And just to do that, we use the same trick. In the Lebesgue sector, we have so we have this constant mu will be equal to mu tilde in the left and right sector. And then this means I have to sum, if you remember, the normal ordering constant came from commuting the operators. No? So we have this infinite sum, which with this factor here, d minus 2, because now we are in the light cone, so we eliminated 2 coordinates. And then we have this infinite sum of n for the bosonic sector. This is from 0 to infinity. And then we have the contribution from the fermions. It starts from 1/2 in the Lebesgue sector. This is the Lebesgue sector. We have this sum. So this sum we can use again zeta function regularization, and then I will use this formula here. I just state the formula. Then we are going to obtain this in a much more physical way. But for now, let me give you a heuristic argument why this is so. So when we have these infinite sums, we can compute it using this zeta function regularization, zeta at -1. It has this one, 1/12 times 6 mu square minus mu minus 6 mu. This one. Okay. Okay, so if we use this formula for this sum, it was done for the bosonic string. It gave -1/12 And then for this sector, for the Neveu sector, since I'm summing over the half integers, I can say, for instance, start at 1 and then add a plus 1/2. So this mu will be 1/2 here. And so, okay, so the result is the following, d minus 2 over 2, and we have minus 1/12 from the bosons. And if we do this computation for plus 1/2 in this sum, which is over the half integers, then we get minus 1 over 24, sorry, plus 1 over 24. There is a minus sign here, so okay, so if we do this, the final result is minus 1 over 16 times e minus 2. Okay, so I will write it here. So we have the normal ordering constant. In the Neveu sector, this is the Neveu sector because I'm summing over the half integers, is minus 1 over 16 and d minus 2. Okay, so I use this regularization. And okay, so and if we do the same sum, you notice here that if we do the same sum in the Ramon sector, it will vanish because in the Ramon sector the modes are integers, so I am subtracting two identical sums. Okay. So we will write it here. This is Schwartz and Ramon equals 0. Okay, so let me first discuss the open string. The open string and the closed string will be a product, basically a product of open strings with the different normalization for the momentum and the level matching condition. Okay, so let me start with the open string. So the mass operator is the level number operator plus the level number of operator, and then I have this normal ordering constant. So okay, so the ground state. We said the ground state in the Neveu sector. So the ground state is the zero oscillator, the oscillator vacuum. So there are the level number operators acting on this state will be 0, and so we only have, if we act here with the mass operator, this gives us the normal ordering constant. Okay.
Excuse me, Professor. What sub-index are in the end?
Here?
Yeah, left.
Here?
Yes.
This means that a transverse, because I'm only using the transverse oscillators. I eliminated the longitudinal. So I act with the mass operator on the ground state, and this gives me just the normal ordering constant. Now the first excited state will be obtained if I act with the lowest number, the lowest mode. Sorry, I am in the light cone, so I only have the transverse oscillator. Okay, so the first excited state, the lowest excited state is the one acting with the lowest operator, which is this B minus half. Okay, so now if I compute the mass of this state, it will be the mass of here will give me 1/2. This each the mass acting on the B operators gives 1/2. Each application of 1 B minus a half contributes 1/2 to the mass square operator. So here I get 1/2 plus the normal ordering constant. Okay. Okay. So this, if you see, this is a vector of SO D minus 2. Okay. So this has D minus 2 indices. This is a vector of SO D minus 2. So this must be massless because of Lorentz invariance. So Lorentz invariance implies that physical states have to fall into the little group, and the little group for the massive states is, in this case, would be SO D minus 1. Since this is a vector of SO D minus 2, it has to be massless. The massless particles fall into representations of SO D minus 2. So this state has to be massless. And then this implies that the normal ordering constant is minus a half. Okay? Which is the same we have computed here. If D equals 10. So if mu is minus a half, this implies D equals 10. And then we obtain this condition again from a physical argument. Okay, so this state has to be massless, and this determines the normal ordering constant and the critical dimension, if we believe that formula. Okay, then so then at the next excited level, we have, so here we acted with B minus half. The next excited level, we can act with alpha minus 1, or we can act with 2B minus half. So Bi, Bj minus half. So each of them increase the mass by 1. Okay, the number, the moding is minus 1. Here it adds each fermionic oscillators adds 1/2 to the mass, so this adds 1 to the mass. Okay, so this gives eight massive states. Okay, this gives 8 states because this again is a vector, and the index I takes 8 values in 10 dimensions, and this here has to be anti-symmetric because these are anti-commuting, so this is 28 an anti-symmetric tensor in 10 dimensions. Yes.
A la cuerda cerrada, la condición de level matching implica que el mu está fijo y vale eso para cualquier dimensión. Menos un 16 por D menos 2.
Sí.
El mu del Nuñez, digamos.
O sea, este argumento es mucho más físico que este. Acá usé un argumento de regularización que, bueno, uno puede creerlo o no. Digamos, acá implica que uno tiró infinitos y se quedó con una parte finita. Se puede discutir, pero es el mismo para la parte izquierda y derecha. O sea, si hago la cuerda cerrada, va a aparecer el mismo valor que va a ser este menos un medio para la parte izquierda y para la parte derecha. Cada parte da menos un medio. Ahora después voy a discutir la cerrada. Pero es lo mismo para cada sector. O sea, la cerrada es una copia de la abierta 2 veces.
Yo tengo otra pregunta.
Sí.
es una duda más bien como para entender. Bueno, hallamos que mu es igual a -1/2. Entonces, ¿eso qué implica para el estado de mínima energía?
Claro, eso implica que el estado de mínima energía es un taquión.
Exacto.
¿Okay? Entonces, de nuevo tenemos un taquión en la teoría de supercuerdas. Tenemos un taquión, después tenemos un estado no masivo y después tenemos una torre infinita de estados masivos. O sea, podemos seguir actuando con estos operadores y vamos a tener niveles cada vez más excitados. Estos estados tienen masa igual a 1, estos que escribí acá. Pero después habrá masas 3 medios y 2 y 5 medios y así. O sea, va a haber una torre infinita de estados excitados. ¿Okay? Bueno, ahora vamos a ver que para que la teoría sea consistente vamos a tener que hacer una proyección que se llama proyección GSO y bueno, un poco también lo expliqué ayer con los dedos, ahora lo vamos a ver en concreto. Si queremos un espectro supersimétrico vamos a ver que hay una proyección consistente que nos elimina el taquión, nos deja un espectro supersimétrico en espacio-tiempo y lo vamos a hacer, en esta clase lo vamos a hacer pidiendo que queremos tener un espectro supersimétrico en espacio-tiempo. Pero si queda tiempo, la próxima clase les voy a mostrar que en realidad la proyección GSO es una consecuencia de la invariancia modular. O sea, hay algo que todavía no se discutió en el curso y que pienso que es importante discutirlo, por eso a la próxima clase lo vamos a hacer. Para que la teoría sea consistente es necesario que tenga una invariancia que se llama invariancia modular y esa invariancia implica que hay que hacer la proyección GSO. O sea, acá lo vamos a hacer porque queremos tener un espectro supersimétrico. Hay también teorías que son consistentes y que no tienen un espectro supersimétrico y que también son invariantes modulares. Pero acá, digamos, vamos a pedir que haya un espectro supersimétrico y eso vamos a ver que nos implica que hay que eliminar el taquión. Bueno, ahora lo discuto. Ok. Entonces, bueno, lo que se puede mostrar... shall I go on in English? Who is for English? Okay. As long as there's one for English. Okay. So all these states will come in multiplets of SO8 because we are in the light cone. So we are only building states with the transversal operators. But one can show that all the massive states can recombine into multiplets of SO9, as it should, because they are massive states, so they can, we can recombine them to be representations of SO9. Okay, so this is so far from the Ramon for the Neveu sector. For the Ramon sector, we have seen that the ground state is a spinor of SO9,1. Okay, but it has to satisfy the massless Dirac equation. Okay, so well, in 10. So first, a Dirac spinor in 10 space-time dimensions has 2 to the 5 independent complex coordinates. Okay, so 64 real coordinates, 32 complex coordinates, and 64 real components. Now on shell, it has to satisfy the massless Dirac equation. So the Dirac equation relates half of the components to the other half. So they are not all independent. So the Dirac equation leaves us with 32 components, 32 real components of the original 64. But in 10 dimensions, we can also impose a Weil or a Majorana condition on the spinors. And each of them reduces in half the number of components. And in 10 dimensions, it is a particular dimension in which we can impose both Weil and Majorana. So if we impose both, this reduces the number by 4, and then we are left with a Majorana-Weil spinor of SO8, which has 8 components. Okay, I will show that. So I said this in words, now I will show you how it works. Okay, so notice that if we are left with 8 components, then we are okay because we have 8 bosons, 8 vectors for the bosonic sector, and then the Ramon sector, which will give us the fermions, will give us 8 degrees of freedom, so we will have the same number of degrees of freedom for bosons and fermions. Okay, so remember a little bit, I won't write this, but remember how we wrote the Ramon ground state. We constructed these operators, these raising and lowering operators, and acting on this on the ground state, which in the light cone, since we eliminated 2 coordinates, say 0 and 1, for instance, so it only has 4 entrances here, the spinor. Okay, so this SI can take plus or minus 1/2 value. So this is a 2 to the 8 over 2, 2 to the 4 component spinor. Okay. And we saw that we can choose the ground state to have 2 possible values of the chirality. We had those with even numbers and odd numbers of -1/2, and these do not mix. So one of them have chirality +1, and the other have chirality -1. Okay, so the ground state I will define. So let me write it here. So I will define the ground state A with chirality +1, and the ground state I will call it A dot with chirality -1. So I act with the chirality operator, this will be +1. And this is chirality -1. Okay? Depending on the number of plus and minus signs. Okay. So so that is this is the ground state, and then at the first excited level, I can act with alpha I -1 on A, or I can act with alpha I -1 on A dot. Okay, but I can also act with D -1 on A, and with D -1 over A dot. Okay, so this is the first excited level. This will be the lowest level. This is massless. And this is the first excited level, which has mass square equals 1. And then I can go on acting with more racing operators. Okay, and again, similarly as in the Lebesgue sector, all the massive states they come into representations of SO8 because I am on the light cone, but they can be assembled into representations of SO9 as corresponds to massive states. Okay. So, as I told you, it can be shown that this theory, with all these states, which contains a tachyon and contains many states, is not supersymmetric in principle because we have 2. So here we have 8 plus 8, we have 16 degrees of freedom in the ground state of the Ramon sector, and here we have 8 degrees of freedom in the bosonic sector. So this spectrum is not supersymmetric in the at the massless level, and there is a tachyon. Okay, so even if we want to keep all these states, and we go and compute the one loop partition function, we will find it is not modular invariant, so unless we perform this GSO projection, which now I'm going to motivate just by saying that we want a supersymmetric spectrum. Okay? So, okay, so here is a table what I just obtained for the Nebel-Schwarz sector. We have the tachyon. The ground state is a tachyon. It is a scalar. It is it can be it is a member multiplet SO9. Then at the massless level we have this vector at the massless level, which is a vector of SO8. Then the first excited level has mass square 1/2, and it is those that I wrote there. This is a vector, and this is an antisymmetric two-rank tensor, which has, as in the representations of the little group, which is SO9, it's as 36. It's 36 degrees of freedom, and at the first level, n squared equals 1. We have all these states, and we can go on forever. Okay. So this is what I just said. And in the Ramon sector, this is what I just said. We have the ground state, the chiral ground state. I will denote chiral with an S and anti-chiral with a C, or A and A dot. So we have these two states. These states are massless. These are spinors of SO8, and these are the representations of the little group. And then the next excited level, we have all these states which can be assembled into representations of SO9, and they are 128 of each chiral. Okay, 128 here and 128 here. In all, there are 256 states at mass level 1, and then we can go on. Okay. So, okay, so we are going to motivate the GSO projection requiring a space-time supersymmetric spectrum. And then you see that at the massless level, if I go back, it is what I said. We had in the Nebel-Schwarz sector, we have a vector with 8 degrees of freedom. So one way of getting the same number of degrees of freedom in the Ramon sector is to eliminate one of the chiralities. If I am left only with, say, A or A dot, then I only have 8 degrees of freedom also in the massless Ramon sector. So, and this leaves precisely the on-shell degrees of freedom of n equals 1, t equals 10 super-Union Mills theory. We have a vector and the partner, which is a Gauchino, a gauge boson and a Gauchino, a massless spinor and a massless vector. But we also want to get rid of the tachyon. Okay? So we are going to do this in the following way. We are going to define an operator, F, which is called the fermion, an operator which counts the number of fermions on the worldsheet. Okay, so I'm going to define this operator, F, which counts the number of fermions on the worldsheet. So basically, it has this one. So if I act with this operator, minus 1, to the F on the states, this operator, according if the state has an even number of fermionic oscillators, will be positive, and if it has an odd number of fermionic worldsheet operators, it will be -1, okay? And I will define the Neveu-Schwarz ground state to have eigenvalue -1. -1. Of course, the Neveu-Schwarz ground state has no fermionic operators, but this is, well, here you can say this is conventional, but the real, so in order to do this, I'm going to define the fermionic number in this way. The reason there is this minus sign here is that if one does a covariant quantization, we haven't done a covariant quantization, but if we want to do a path integral quantization, we have to introduce the ghost to compute the Fadeev-Popov determinant, which are anti-commuting ghosts in the bosonic sector and commuting ghosts in the fermionic sector. And if we include the ghost will contribute this -1. Okay, so if you want, for now, just take it as a definition. I'm taking the Neveu-Schwarz ground state to have eigenvalue -1 of this operator. Okay, so so notice that if we are left with the state, so this here, I write which is the eigenvalue -1 to the f. This I said has -1, but this here, since I have one fermion, one worldsheet fermion, it will have -1 to the f equals 1. Okay, and the next one, this one has no fermion oscillators. This one has 2, so this has even number of fermions on the worldsheet. So again, this will have -1 to the f -1. So if I define the GSO projection as GSO projection implies to keep only states for which -1 to the f is equal to +1. In the Neveu-Schwarz sector, I get rid of the tachyon, but I also get rid of all the states which have here. Oh, this is sorry. This has 0. Yes, this has sorry. The mass square is a half, no? Because we had the non-arbitrary constant here. So if I keep only the operators with -1 to the f equals +1, I get rid of all the states in the Neveu-Schwarz sector which have half-integer values of the mass. Okay, I'm only left with and notice that these states have no partners in the Ramon sector. So if you look at the masses in the Ramon sector, the masses are all integers in the Ramon sector. There are no half-integer masses. So by doing this, I have a chance of getting a supersymmetric spectrum.
Si vos quitas así de un estado, las cosas interactúan.
Bueno, claro, hay que asegurarse que en las interacciones no aparezcan los estados que estoy eliminando. Sí. Y efectivamente eso se puede ver. Sí, bueno. GSO is Gliozzi, Scherk, Gliozzi, Scherk, and Oli. This is 1977. Results. Okay. So this is So in the a general state in the Neveu-Schwarz sector, a general state will have a certain number, say n -1. It will have, for instance, n oscillators, n bosonic oscillators. and let's say n fermionic oscillators. So a generic state will have, so only to determine the eigenvalue of minus 1 to the f, we only need to count how many fermionic worldsheet, how many worldsheet fermions we have. So this state has eigenvalue, so minus 1 to the f will be minus 1 to the m. M counts the number of fermions on the worldsheet, plus 1 because I define the ground state to have minus 1. Okay.
How do you define this proyecto?
Sorry?
How do you define this proyecto?
It's here.
No, this is a, but how do you define the proyecto in the set?
So I just say that I keep states that have minus 1 to the f equals 1.
Yeah, but there is a way to define, when defining proyecto, to kill the set and keep only the set with this.
No, I mean, this,
Sí, no es,
I just,
pasando de lado y aplicando los resultados, los que no te cumplen eso, no sé, uno más menos uno. O sea, pero lo consistente sería definir un proyector que mate los estados estos y que deje solo los, o sea, es un espacio vectorial.
El proyector es 1 menos eso.
Claro, pasando de lado.
okay. Fine. So what about the Ramon sector? This was for the Neveu-Schwarz sector. In the Ramon sector, we have to define a generalized chirality operator because we also have the zero mode. And then the equivalent of this minus 1 to the f in the Ramon sector is called the generalized chirality operator, which is this is in the light cone. Okay, this 16 is conventional, and then depending on how one normalizes. So this is in the light cone. I only have the transverse zero modes, and then minus 1 to the f, which now has integer modes. Okay, so again, this counts the number of PIs in the state, and this is the chirality operator. So depending on which, so this is the fermion number, and this is the chirality operator. So the eigenvalue of minus 1 to the f will depend on how many fermionic oscillators the state has, and also the chirality of the ground state on which they are acting. Okay. So one can show that this operator anti-commutes is very easy. With sine u. Okay, so the eigenvalues of the Ramon ground states are plus 1 or minus 1. The Ramon ground states have no oscillators, fermionic oscillators, so the eigenvalues of minus 1 to the f will be plus 1 or minus 1 depending on the chirality. Okay, so a generic state in the Ramon sector. if it is acting on the chirality 1 or -1, but the eigenvalue -1 to the f will be -1 to the m, because this part just counts the number of this, and then -1 to the sum over I of delta mi. So this will count the number of B0 operators acting on the state. Okay? So this is the eigenvalue for a generic state.
La motivación de esto de la proyección GCO era para quitarnos el tachyon.
Es para, o sea, es para tener un espectro supersimétrico. Y en particular nos quita el tachyon. O sea, si hacemos una proyección así, nos quita el tachyon.
Porque en Ramón
No hay tachyon.
no hay tachyon.
Pero bueno, fíjate que en el estado fundamental nos elimina uno de estos. En el estado fundamental teníamos 16 grados de libertad de Ramón y 8 de Leve-Schwarz, o sea que no es supersimétrico, hay más grados de libertad fermiónicos que bosónicos, y con esta proyección matamos la mitad.
Va con signo más el proyector para que mate a los que tienen que matar. Si no, está matando a los otros.
¿Cómo?
Sí, tiene que ser +1, el 1 a la F +1 para que mate a los otros.
Sí.
+1.
Te está diciendo ahí cuando lo vimos antes. -1 la F +1.
No.
Sí, porque mata a los buenos.
Este es el Leve-Schwarz, porque el vacío de Leve-Schwarz lo definí con un menos. Esto es una definición. El vacío de Leve-Schwarz no tiene... Pero en Ramón no. O sea, en Ramón es esta parte lo que le da la quiralidad del fundamental.
Es eso, es más bien que el proyector para que mate los estados que tienen que ser con -1 a la F +1, porque si no mata a los buenos.
Le está señalando
¿Qué son los buenos?
le está señalando el P.
Ah, ok.
Y hay que dividir por raíz de 2.
Perdón. Okay.
Y hay que dividirlo por raíz de 2 para que sea muy bueno.
También. Claro.
Sobre 2. Sobre 2.
Cuando yo mato menos uno. So this is the eigenvalue. So this is the eigenvalue of -1 to the f when the operator acts on the chirality 1 ground state. But of course, if it's acting on the chirality -1, then it will get a -1. So plus or -1, and +1 is when the ground state is chiral, chirality 1, and -1 when the ground state is chirality -1. Okay, so the GSO projection then amounts to keeping all the states that have in the Ramon sector, no? That have eigenvalue +1 or -1 of this operator -1 to the f. I can keep either those which have chirality +1 or those which have chirality -1. The spectrum will be supersymmetric. Okay, of course, consistency requires that the interactions, the states that I killed do not appear in the interactions. And and this follows because one asks in the operator algebra of the vertex operators that these states do not appear. Okay, so to obtain the spectrum of the closed superstring, we have to take the tensor product of two sectors. This, so far I have done everything for the open string. For the closed string, I have to take products of left and right and impose the level matching constraint. Okay? Okay, so as I said, there are four sectors, Leve-Schwarz, Ramon. This will give space-time bosons, and Leve-Schwarz, Ramon, Leve-Schwarz will give space-time fermions. Okay? Okay, so we can choose two possible chiralities for the left and the right ground state. for the Ramon sector. And, okay, so if I do this in the Neves sector, so in the Neves sector, I take for the left mover this ground state, and for the right mover, the same thing, okay? So I take this product of two ground states. Each one is a scalar, so the mass is -2, because I have a -12 and -12, a -12 for the left moving part, a -12 for the right moving part, and also a different normalization for the momentum. Okay? Recall that for the open string and the closed string there is a factor 2 in the momentum, square root 2 rather. So the mass square of the ground state in the closed string is -2. And again, this is a scalar of SO9, which is the little group of massive states. And at zero mass level, I have, again, a product of, so I have a B minus a half acting on the ground state times the same thing. So these two things, they have the same mass. So, okay, so this here organized into multiplets of SO8. And one sees that this representation can be decomposed. So this is basically a tensor, and it can be decomposed into a scalar, an antisymmetric rank 2 tensor, and a symmetric rank 2 tensor. Okay, so this will be the standard sector, which, as you see, it disappears in all string theory. We have this universal gravity sector, which appear in all consistent string theory. This will give rise to the dilaton, the antisymmetric tensor, and the gravity. This, we cannot avoid these states in any string theory. Okay. Now, for the Ramon sector, again, we can take products for the ground state. We can take two chiral 1, chirality 1 and 1, chirality -1, -1, -1, +1, +1, -1, all possible combinations. And this product of, these are spinor representations, so I think you have learned with Nathan that if you have a product of spinors, then it can be decomposed into tensors, into sums of tensors. So, and it depends on the chirality. So if you have a product of chiral, of spinors of the same chirality, then you get this decomposition. So you get a scalar times a rank 2 antisymmetric tensor times a rank 4 self-dual antisymmetric tensor. Okay? When you have the product of chiral or anti-chiral. Whereas if you take the product of a chirality 1 and chirality -1, or the opposite, then you get this decomposition. You get a vector with 8 components in SO8, and this here is a rank 3 antisymmetric tensor, okay, which has this number of degrees of freedom. Okay. Questions? Okay.
Bueno, esta refería a la parte de NS que estuvo hablando. No sé si me entendí muy bien. Dijo que cuando se aplica sobre el vacío de NS, el vacío operador -1F debe tener menos por la contribución de Gauss, ¿cierto? Entonces, de esta manera es que usted escoge que va a eliminar aquellos que deben tener más, o sea, los que deberían dar como +1 delante del vacío de NS, los mata porque no,
mato los que tienen -1. Elimino los que tienen -1. Con eso elimino el taquión y bueno, y todos los estados en Neves-Schwarz que tienen masa semientera, que no están en el sector de Ramón, no hay estados con masa semientera. Entonces nunca voy a poder tener un espectro supersimétrico si mantengo los que tienen masa semientera.
Sino que ellos se había puesto una de las viscosidades que para esos casos ellos no había términos de casos comparables.
claro.
Como los mata no hay fermiones, o es que...
No, es que no hay. Si construyo, o sea, los estados que construyen el sector de Ramón, todos tienen masas enteras, masa al cuadrado entero. No hay ninguno que tenga masas enteras. Okay. Now, the Ramon-Neveu-Schwarz sector. So we take a product of Ramon for the massless states. We take a ground state, Ramon ground state times zero mass Neveu-Schwarz state. And again, we can take chirality +1 or chirality -1 state in the Ramon sector. And then this gives us, so this is a spinor times a vector. So this will give us a spinor, fermionic state, which as representations of the little group, this will give us an 8-component chiral or anti-chiral spinor plus gravitino. So this will be the gene, let's say, and this will be the gravitino. So, okay.
Estoy confundido con la pregunta que hizo él. Entonces, ¿uno quiere que los tengan los dos sectores al mismo tiempo?
Uno siempre tiene todos los sectores, ¿no? La teoría tiene todos los sectores. Lo que estamos haciendo es eliminar algunos estados. O sea, si los construimos así de manera naive, el espectro que resulta no es supersimétrico. Entonces estamos eliminando algunos, pero aparecen todos, los 4 sectores, Neveu-Schwarz, Neveu-Schwarz, Ramón-Ramón, Neveu-Schwarz-Ramón y Ramón-Neveu-Schwarz en la cuerda cerrada. Y en la abierta aparecen 2, Neveu-Schwarz y Ramón. Okay, and the same thing for Neveu-Schwarz-Ramón is basically the same. I just switch right and left. So the massless Neveu-Schwarz state and the Ramón state, and they only depend on the chirality. So the result here is also depends on the chirality. Okay, so and if we look at the, okay, now we look at the eigenvalue of -1 to the f. So, okay, so if I want to construct the first excited level, there are too many states to write them here. It is one of the exercises that I propose for you. So it's just acting with creation operators and then okay, applying the GSO projection to those that we don't want. So how does the GSO projection works for the closed string? There are 2 possible ways to do the GSO projection for the closed string. We can take -1 to the f. So we have here a fermion operator for the left movers and a fermion operator for the right movers. So we can take that they are both equal or one is opposite the other. So we can take -1 to the f equals 1 and -1 to the f tilde equals 1, or -1 to the f equals 1 and -1 to the f tilde equals -1. So this difference, the difference between the 2 choices will give rise to what are called the type 2b and type 2a theories. So if I take the same chiralities on both sides, I get the type 2b theory, which is a chiral theory. And if I take opposite chiralities, then I get the 2a theory, which is not chiral. So it has a chirality +1 on the right sector and -1 on the left sector. Okay, so let me just display here. This is finally the result. So I will write this on the blackboard, because this is important. So for type 2b, we take -1 to the f equals 1 on both sectors, left and right. And then let's do the following spectrum. In the bosonic sector, we have for the bosons. In the Neveu-Schwarz sector, we have the dilaton, the antisymmetric tensor. I'm writing here the dimensions of the states. Okay? And the graviton. This is in Neveu-Schwarz sector. And in the Ramon sector, remember, I'm taking those which have chirality +1. Okay, so this is chirality +1 times chirality +1. It gives me these tensors, which is rank 0 tensor, plus rank 2 tensor, which has 28 degrees of freedom, plus a rank 4 antisymmetric tensor, which is self-dual. So I write here the +1 to indicate that it is self-dual. Argentinians, do you have questions?
No, una pregunta nomás. ¿Puedo decir que son iguales los -1 a la F, además son iguales a 1 o a -1?
A 1, pueden ser a 1 o a -1, no importa, o sea, para la descomposición en términos de...
¿No da dos cosas distintas? No.
No, lo que da distinto es si tomas 1 y -1, pero si tomas 2 unos o 2 -1. La descomposición en tensores, ¿no? Okay, so this is... and for the fermions, we have the 8. I call it C for this chirality. It could be C or S, either one. Ramon plus C plus 56. So I can take both with C was chiral or antichiral, or I can take both S and it's the same. So this, if I add up the number of degrees of freedom, these are 128 in the bosonic sector and 128 in the fermionic sector. So this is a supersymmetric spectrum. And this is the spectrum of the type 2B. It is the same spectrum of type 2B supergravity. Type 2B supergravity. It is type 2 because it has 2 gravitinos. So the number of gravitinos determines the number of supersymmetries, and this theory has 2 supersymmetries because it has 2 gravitinos. Okay, so yes. Oh, okay. Okay, I think I already said this, but then in the bosonic sector we have a scalar, which is the dilaton, antisymmetric rank 2 tensor, which is the antisymmetric tensor, symmetric rank 2 tensor, which is the graviton, and then we have a vector in the Ramon sector, a vector, antisymmetric rank 2 tensor, antisymmetric rank 4 tensor, self-dual. It satisfies a self-duality condition. Okay, so this is for the bosonic sector, and again in the fermionic sector, as I already said, that we have 2 gravitinos, so this implies n equals 2 supersymmetry, and the 8s are spin 1/2 fields, which are called dilatinos. They're the fermionic partners of the dilaton. Okay. Yeah, the dilaton, and notice here we have another scalar from the Ramon sector. Okay, so again, we have the same chirality left and right, so this is a chiral theory. And the type 2A, this is type 2B, and type 2A again, for the bosonic sector, it is the same. It is always the same. Any string theory has this sector, which is a dilaton, antisymmetric tensor, and graviton. But in the Neveu-Schwarz, in the Ramon sector, since we have a chiral antichiral spinor, instead of having the even rank, the even rank tensors. We have the odd rank tensors, so we have a vector, rank 1 tensor, plus a rank 3, again I call it vector, a rank 3 antisymmetric tensor with round Domin sector. And for the Fermi sector, plus, and now we have one chirality on one sector and another chirality in the other sector. Again, we have 128 degrees of freedom in the bosonic sector and 128 in the fermionic sector, and this indicates a supersymmetric spectrum. And this is the same, the field content of type 2A supergravity. Again, two supersymmetries. Okay, let's see this again. I have already said this. I'm out of time.
Because yours went out.
So if you are not tired, you can go. Okay. Good. So this allows me to do the third superstring. So we have found now two consistent superstring theories. We have seen the spectrum of 2A and 2B. And now I'm going to construct what is called the type 2A, the type 1 theory. So I am tired. Type 1 theory. So one thing we have not yet discussed is the possibility of defining an orientation on the worldsheet. Okay. So even after choosing the Lightcomb gauge, we still have some freedom. So the original reparametrization invariance has not been completely fixed, because we can do a worldsheet parity transformation, which is a discrete transformation. I can send sigma to minus sigma. So sigma is the coordinate along the string. So I can do this transformation. Sigma and tau. Okay.
You're doing so well.
No, this is a good point to start. I've already done the
So maybe there are some 5 minutes at least for questions.
Tenemos tanto en la cuerda abierta como en la cerrada, y aún después de aplicar la proyección, tenemos los distintos sectores al mismo tiempo en la teoría, ¿no? Y tenemos distintos vacíos en cada uno de los sectores. Y eso, bueno, yo no lo encuentro como... Bueno, es que, ¿cómo podemos tener dos vacíos en la misma teoría?
Y en cualquier teoría de campos, ¿no? Uno tiene distintos campos y cada campo es...
O sea, así es como lo debo interpretar justamente, porque eso es lo que no veo.
Claro, sí, uno tiene todos estos campos, o sea, la teoría tiene todos estos campos no masivos, y bueno, cada uno tiene su estado fundamental. Después, bueno, también están todos los masivos. Acá me discutí básicamente los no masivos, pero bueno, están todos los masivos y cada uno se construye a partir de su estado fundamental. Pero es lo mismo, o sea, en una teoría de campos es lo mismo, ¿no? O sea, uno tiene estados bosónicos, estados fermiónicos y cada uno...
¿Cómo se define la función de partición a un lazo
en la teoría de supercuerdas? ¿Cuál es su utilidad?
Lo voy a discutir en la próxima hora, cómo se construye. Se construye básicamente igual que en mecánica estadística, o sea, bueno, exponenciando el operador, el hamiltoniano, que describe cómo evoluciona la cuerda en el tiempo, y definiendo también un operador momento que nos traslada los estados de la cuerda en el loop. Entonces, básicamente se define así. Bueno, hay algunas complicaciones técnicas para calcularlo, pero bueno, justamente tiene que cumplir algunas propiedades, que es esta propiedad de invariancia modular, de la cual espero poder hablar en la próxima hora, que es lo que es una de las condiciones de consistencia de la teoría, y es lo que implica que haya que hacer esta proyección GCS para tener una teoría consistente, que quiere decir una teoría invariante modular. La función de partición, básicamente, la función de partición es la función en la cual no hay ninguna inserción de operador de vértice, la integral a un loop sin ninguna inserción de vértice. Y básicamente lo que contiene es el contenido de campos de la teoría. O sea, uno puede hacer un desarrollo de la función de partición y eso va a representar todos los estados que aparecen en la teoría. Va a ser una suma infinita de estados que le va a dar la multiplicidad de cada uno.
Nos mencionó que la invariancia modular es una exigencia para que las teorías sean consistentes. Bueno, por una parte, ¿qué es invariancia modular? Y bueno, y después de eso nos dijo que esto implica la proyección SO.
Podríamos quizás discutirlo después de la próxima clase, porque voy a dar toda una hora de eso.
Is there another question? If not, so